Hello.
Hi, Giovanna, John.
Hi.
How are you?
How are you?
Good morning, everybody. Okay, well.
I'm glad I got connected, okay?
Yeah, it's good.
Yeah.
We're glad you could make it, John.
Yeah, glad to be here.
Yeah. Hey, Antonio, I was just kind of curious. Can you record this webinar so you can use it to read it later if you
I did that. I don't understand. It was a miss hearing. So the question is if we can save. I mean record.
Yeah, if you can record the webinar.
For sure.
And then you can save it and you can use it later if you like.
Yeah, for sure. We will do that.
Okay, great, fantastic.
I'll be right back.
John, could you try to share your presentation in order to?
I can now if you want me to. Let me see. Let me share screen.
Okay, we're seeing.
Okay, you're seeing one slide. I had it open. Slideshow from beginning. How's that?
Yeah, very good.
Perfect.
Let me make sure everything's working. Yeah, looks like it's working okay.
Yeah. Let me say something. There are a few people from environmental labs. It is not the focus of this seminar, but in some environmental labs wants to move from the traditional cyanide photometric with distillation the method, but they are aware about the validation process because in some regulation here in Mexico, it is required the photometric method for cyanide in water. We trying to explain the convenience to move to the amperometric with gas diffusion, membrane diffusion device, but they are aware about the validation process. So I think you can only mention in this presentation the advantage of using the amperometric with gas.
Oh yeah. I focus a lot on that.
Okay.
A lot. Specifically. But correct me if I'm wrong, G, but don't we do system validation, IQ, OQ, PQ for cyanide systems?
Yes, there is for the cyanide. There is a IQ/OQ package that we use it for clinical. Yeah, for the market. Yes, it's available. Yes.
Yeah, that's something that we do.
Yes.
Yeah, but the lab manager and the technicians at the lab must do their own validation process after the qualification, and that's the steps that they want to avoid.
Oh.
But it is a must. So they don't want to do that. It is a must.
Yeah, right. Okay, I gotta step away for just a second.
Okay. No, let's just wait 5 minutes or more to begin. Thank you very much, everybody.
Antonio, I thought we sold one cyanide system. I think was that the city of Juarez, I think that required the validation, correct?
Yeah, that's right.
Okay. So would that validation be something appropriate for the environmental customers also, or is it something different?
No, no, it's for environmental.
Or specific to environmental?
Yeah. Yeah, but let try to discuss that later with the salesman in order to
Okay. Mm-hmm.
to be sure all of things.
Yes. Uh-huh.
Thank you. Buenos días a todos los que ya se han conectado. Cecilia, Cintia, discúlpame, Eleonice y Felipe. Perdón, no podía pronunciar bien. Bienvenidos. Vamos a empezar justo a las 10 de la mañana, hora del centro de México. Como se dieron cuenta, ya están conectados nuestro panelista y pues vamos a empezar en unos minutos más. Mientras, bueno, pues muchas gracias por estar presentes. Para quienes ya se conectaron, el micrófono va a permanecer cerrado y todas las preguntas y comentarios, dudas, van a ser hechas por el chat o por la sección de preguntas y respuestas de la aplicación de Zoom. Entonces, en unos minutos más, arrancamos. Muchas gracias por estar presentes. Buenos días a todos los que se han conectado. Bienvenidos. En unos minutos más iniciamos. Gracias por su participación. En unos minutos más iniciamos con nuestra presentación. Gracias.
Recording in progress.
Hola, muy buenos días a todos. Muchas gracias por su participación, por estar presentes en este seminario. Mi nombre es Antonio Camacho, yo soy responsable en Analitech del soporte y asesoría para todos los productos que manejamos. Y el día de hoy tenemos la participación del doctor John Welch de OI Analytical, y en este momento vamos a trabajar con un seminario que, si bien ya hemos compartido información meses atrás, nos parece muy importante volver a tocar el tema. Este seminario está enfocado a el análisis de cianuro. Es un proceso pues muy importante en el procesamiento de mineral de oro y de plata. Y el enfoque está dado lo hemos seleccionado hacia equipos o sistemas de mesa para uso en laboratorio, pero también para sistemas en línea. El doctor John Welch tiene una amplia experiencia y una formación en química analítica ya muy vasta, con pues una buena cantidad de trabajos, asesorías y publicaciones en este campo. El seminario se va a dar en inglés. El micrófono va a permanecer cerrado Todas las preguntas las pueden hacer vía el chat de la aplicación o a través de la sección de preguntas y respuestas de Zoom. Para quienes nos siguen por YouTube, pueden hacer las preguntas a través de correo electrónico en la dirección de la invitación que les llegó y la confirmación del acceso a este seminario. Yo voy a traducir las preguntas que ustedes nos hagan y ya para que el doctor John Welch nos pueda contestar y hacer las aclaraciones que se necesiten. Entonces, bueno, iniciamos. Vamos a tener un momento para las preguntas, como les comento, pero en cualquier momento pueden escribirlas y ya los voy preparando yo para hacérselas llegar al doctor. Good morning, everybody. Dr. John, ready to run. Thank you. Thank you very much.
Oh, you're welcome. So do I share my screen now? Okay, hold on just a second. Uh-oh. Please move this window away. There we go. Hold on just a second. Okay, can everyone see my screen?
Yes.
Okay, very good. Thank you for the introduction. Again, my name is John Welsh. I am a product manager with OI Analytical, and it is my pleasure today to introduce to you and present to you the solutions that OI Analytical has for cyanide determination, specifically for the mining process in both an online setting and in the laboratory, because we use very similar technologies in both places, which have proven to be very effective for this application. So with that, I'll get started. What I will cover today is cyanide determination by gas diffusion and amperometric detection. That is the heart of the OI methods. The OI Analytical Model CN Solution 9310, which is the online analyzer. The cyanidation process and interferences. Some other comments on other analytical methods, and the OI Analytical Model FS 3700, which is used in the laboratory analysis. So again, we'll start with cyanide by gas diffusion and amperometric detection. In the mid-1990s, it was recognized by people in the field, particularly in the mining applications, that some of the existing methods for cyanide determination were lacking in terms of their ability to effectively measure cyanide, particularly at low-level concentrations, due to a number of things, these being interferences, different difficulties with different techniques. So starting then, in cooperation with the University of Nevada, Reno, the Mackey School of Mines, OI Analytical developed what is known as OIA 1677. The OI stands for OI Analytical, and this is the method in the United States that is in the Federal Register with the EPA as the accepted method for determining available cyanide. And from this method, this being the groundwork for all other methods that followed, other methods were developed for free cyanide and total cyanide. So this is the heart of the basis by which OI Analytical instrumentation determines cyanide. Gold and silver is extracted from ores using cyanide solution. The gas diffusion amperometry methods for free, available, and total cyanide were developed because they are the only methods known capable of accurate determination of cyanide in these matrices. OI Analytical offers both laboratory and online solutions. Again, as I mentioned earlier, ASTM D1677, which is also OIA 1677, has these characteristics. It is a non-distillation technique that provides accurate measurement of available cyanide. A sulfide removal acidification agent is added in line for the removal of thiocyanate, sulfite, and thiosulfate interferences. Mercury and nickel cyanide complexes are not covered without pretreatment of the sample and without ligand exchange reagent. Mercury and nickel must be treated a little bit differently. OI Analytical chemists have also recently made improvements to one of the subsequent methods, and I'll talk about that a little bit later, D7511. The addition of acetic and ascorbic acid to the existing acid reagent nearly doubles the response. The CN Solution 9310 schematic here showing FIA gas diffusion amperometric method. The way this method works is we have 3 reagents, sometimes 4, depending on what we're doing, but always a base, acid, and a carrier. The sample is introduced by a pump through a sample loop and then injected into the acid stream, mixed prior to the gas diffusion membrane. So at the top of the membrane, the base is always flowing. At the bottom, the sample and the acid are mixed, and this produces hydrogen cyanide. The cyanide diffuses across the membrane where it is swept up into the flow of a base, typically sodium hydroxide, and then to the detector and ultimately the cyanide waste. The acid waste goes to a separate container. This is fundamentally the approach by both the online and the laboratory instrumentation. So acidification step, down here at the bottom, we produce hydrogen cyanide gas. It diffuses across the membrane, and there it reacts across a silver electrode by this equation here, and thereby giving us a reading or in proportion to the amount of cyanide that was in the sample to start with. It's a very, very simple, easy to use approach that eliminates a lot of the technical difficulties that might be associated with other techniques. Available cyanide by gas diffusion is very similar. As a matter of fact, it's almost identical. If we were doing, for instance, free cyanide, we would eliminate the acid step here. But by method definition, this is very similar to the WAD cyanide or weak acid dissociable cyanide. This is actually a schematic from the laboratory instrument, and it works in principle very much the same way as the online instrument. And lastly, all of these methods, ASTM D6888-09, it's a little bit different than the previous ones. Again, the point here is that in 1677, we started with one technique and built on that as the need for the determination of different cyanide species became necessary. Again, the basic steps, base reagent, carrier, but in this case, particularly for some of the compounds that only react with a ligand exchange reagent, then a ligand is added in this port here to the sample, then a mixing coil, then the acid reagent, and then finally to waste. This ligand is necessary for some species that are difficult to determine with just, say, an acid reagent. That's the basis of ASTM method D6888. So additional methods, as I mentioned before, I showed you the schematics of how those work that came about after 1677. ASTM 6888 is the standard test method for available cyanide with ligand displacement and flow injection analysis. That is the regulatory definition of that method. It utilizes, again, gas diffusion separation and ampere-metric detection. ASTM 7511-12 is the standard test method for total cyanide by segmented flow injection analysis, inline ultraviolet digestion, and ampere-metric detection. I think I have a schematic of this one coming up a little bit later. In this one, in addition to the reagents that are used, there is also an inline UV digester for digestion of the very hard to oxidize or digest samples. And then OI analytical instrumentation, the CN3700, CN9310, conforms to all of these methods in addition to OIA 1677. And I'll start first. The previous slides gave you a background of what we're going to talk about now with the individual instrumentation. We'll start with the online instrument, which is the CN9310. This was designed and built and tested in cooperation with Newmont Mining Corporation, specifically for the precious metal extraction process. Gas diffusion selectively separates CN from matrix and detects without interference. Calibration is accomplished in 2 to 3 minutes. We can monitor up to 4 sample streams with ports for 0 and span calibration standards. A color touchscreen with a very intuitive user interface is available to the operator of the instrument, and it can connect via LAN connection and be run remotely from any computer in which we have our control software installed on. It measures available cyanide for precious metal leaching solutions by the methods we had just discussed, 1677, 6888, and ASTM 7511. Concentration range is less than 100 ppb, up to 2,000 parts per million are available. A range of configurations to match the installation site are also available. A unique sampling system that was designed specifically for processed slurries is also available. And it can be used as a laboratory setting for fast screening of samples. What I mean by that, of course, the majority of these instruments are in a process setting. However, this instrument could be set up on a freestanding rack in a laboratory and run much the same way as you would an online instrument. You would simply just put your samples underneath the instrument in separate containers, and you can select and do it that way. It's flexible in that regard. This shows the inside of the CN9310. One comment about this picture, it's a little bit older picture. The newer instruments have a diaphragm pump, not a diaphragm pump, a peristaltic pump that sits here now, as opposed to the diaphragm pump that's on this valve manifold here. That's the only difference. What you see down below are 1, 2, 3, 4 sample stream ports that are available, and these two would be used for calibration. This is the valve manifold, which injects the various chemicals such as the base, the acid, and the carrier. Up here is where the sample loop, or the valve with the sample loop, is located. And down here is the gas diffusion membrane. We have the base that comes across the top of the manifold, the acid and sample mixture, which comes to the bottom. And out of this, it flows directly into the amperemetric flow cell, which you see here, and which, by the way, we'll mention a little bit later, is the same flow cell with just a slight modification for the higher ranges that we might do on the process instrument that is also used in the laboratory instrumentation. That was just brought over into this, because this really is the heart of the instrument right here, this detector. All things are, this is very good. Yes.
Yeah, there is a window in the top of your screen. Could you move it?
Oh, I'm sorry. I didn't know you could see. Oops. Hold on just a second. Did it go away? Oh, no. Let me see. Please move this window away. I'm trying to figure out a way to move it. It says move it away, but I can't make it go away.
Okay, well,
I'm sorry. Okay. Yeah, yeah, it wasn't there earlier.
Yeah.
And I don't know. Oh, I'm sorry.
It's okay.
Before I started to move this away, but it wouldn't. Okay, well, I'll have to keep going then. I don't know where it came from. So again, we've seen this schematic before. It's exactly like the one that we saw in the previous slides as far as the flow path goes for this instrumentation. And this is a more detailed look at of how the CN9310 works. And just very quickly, this valve will rotate to whichever port which is called out in the sequence of what we want to measure, whether that be the low calibration standard, the high calibration standard, or one of the sample ports. When that is selected, this pump turns on and fills the sample loop with the representative sample. When the instrument is ready to analyze the sample, the valve rotates. Then DI water, which is used as the carrier, pushes the sample into this path where it comes in contact with whichever reagent that we need to react it with. Most commonly, that would be acid, which would be the first one. If necessary, we can populate this with a valve to inject ligand as well too. And then finally, this flows again, as we've seen, across the bottom of the gas diffusion membrane. The base valve turns on, keeps the flow of sodium hydroxide across the top, and then that sweeps it up into the amperemetric flow cell and ultimately at the waste. So at the bottom, we have the reagents that we need and these components to make the analysis. And finally, that signal is sent over to the amperemetric detector on the electronics, and we get our signal from the instrument. Some of the system components, this is a picture of a basic CN9310 system, particularly for an outdoor location. It's housed in a 316 stainless steel enclosure. We have available optional air conditioning units for very hot climates if that's necessary. And what you see here on the left-hand side is the pump control module, which is controlling, in this case, these two pumps, because in this application, we were doing 2 streams. I'll show on a subsequent slide the sample filtration probes, which are not shown here. On this side, the pumps would push the sample into these sample inlet devices. And when that stream is selected, then as we saw in the previous slide, the sample pump on board the instrument pulls the sample out of here and then through the flow path of the instrument. So what comes with the system, again, with the filtration probes, is the tubing for the sample filtration probes, and then this is a complete solution in one package. So we have the CN9310, the pump control module. This is for control of the sample probe, which I'm going to show you in a slide. And down below it would be our reagents, check standards that we need here and would plumb to the instrument. So this is more or less a very basic system for the CN9310. Here's a picture of that system, except in this instance, it was not housed in a stainless steel enclosure. There was a shelter built over the instrumentation, and up above it, it's covered by other parts of the plant. And this one was up in the mountains of Peru, I believe. And it's rather cool climate, so we didn't have to really be concerned about any high temperatures. But again, you see the basic components once again. The analyzer, pump control module. This time there was just one pump. And down below it here, and these are spare chemicals for up here. And you see all of the reagents and standards that are mixed here. This is, again, one possible configuration that we can offer for the instrument. As I mentioned, as part of this package, there is a sample probe assembly. And at this end of it, we refer to it as a filter sock. It's a membrane that slips over this housing here. And down this tube are 2 lines. One is for pulling the sample. The other one is for injecting pressurized air into this assembly, thereby pushing off the slurry that might be covering the filter. And then once that pressure is relieved, the liquid flows into this support. And when the pump is ready, or when the instrument is ready, the pump turns on, pulls the sample out of here. So if I go back a couple of slides, if you see here, this is what controls the air pressure to this device to clean this filter off and then allow the sample to flow in and then be pulled by the pump into the sample inlet devices in the instrument. These are removable and serviceable. They will need service after some length of time. But this is supported by this long pipe here and this lifting hook. So what happens is you pull this out of the slurry, service this end of it, and drop it back down again. And here you see that. This is a technician raising or lowering the sample probe. Here's the hook that holds it here. This is the pipe that supports it. There is the filter element at the end of it, covering the collection device at this end of it. So this was designed for slurries with up to 60% solids. It's a polypropylene cover that filters 210 micron. And as I showed in the previous slide, compressed air from the pump control module provides a blowback. It clears the cover before the sample pulls in, and then the pump turns on and pulls the sample into the instrument. So this is raised and lowered down into some point in the slurry tank to pull the sample into the instrument. And where in the process have we done this? In a number of places. At the we've done as far as in both the leaching process where cyanide is added at higher concentrations, and at the typically what we will do is at the detoxification end at the lower level, there'll either be one stream from here or one stream here or one instrument here or one instrument here. It could be placed in any part of the process, but these are the two primary places that we typically install this instrument, one for the process control from the front end, and then for measuring the cyanide destruct or detoxification before that liquid goes back into a tailings pond to be further treated. This is data from, or typical data from an instrument, actually from 5 different instruments from the 2 ppm to the 200 ppm level. As you can see, the precision and accuracy of the instrument is very good, and this is pretty typical. This is just the range up to 200. We can go up as high as 2,000 parts per million, and we have done in some applications below 100 parts per billion as well too. I know I've focused mostly on the process side, but in addition to that, we have deployed CN9310s for environmental purposes, meaning we have installed these on streams flowing away from a gold mine or mine, any mine, where we're actually monitoring the water to ensure that there's no breakout of cyanide to the surrounding waters around the plant. Again, this is the repeatability of the instruments in that range. And some of the lab versus 9310 data, because this is one of the benefits of the OI analytical approach is that we use the very same technology in both locations. There would not have to be any adjustments necessarily for compensations for different types of techniques. It is the same technique that's used in both places. And as such, it would be interesting, or was interesting to know, to make sure that our lab data versus our 9310 data with representative spike samples does indeed match. And they do if the instrumentation is set up and calibrated the way it should be. Again, this is correlation from the laboratory data, which you see is very, very good. And lastly, in a typical process, this is typical process data where we are measuring after being dosed how the cyanide is being consumed by the process all the way down, starting at where the cyanide was added to the process, then it spikes up, it's being consumed, and coming all the way down to the approximately 60 part per million range. So that was the CN9310. And before we talk about, or I talk about the lab solution, I'll come back and talk about cyanidation and interferences, because it was the issue of interferences and some of the difficulties with other techniques that ultimately led to the creation of OIA 1677 and all the other subsequent methods. The very basic alkaline cyanide solutions are preferentially dissolved precious metals according to this equation. This is the basic equation for gold extraction, where you have gold and sodium cyanide and form this among other complexes with gold and sodium hydroxide. And the rate of gold dissolution is dependent upon many things. The cyanide concentration, dissolved oxygen, alkalinity. The optimum cyanide concentration is 0.02 to 0.05%. Optimum dissolved oxygen concentration, it does vary by the mineralogy and process steps. And typically the optimum pH is around 10.5. And all the instrumentation was designed with these considerations involved. I mean, the instrument operates at these very high pH, especially. So a multitude of cyanide species of varying stability may be present in a sample. That's one consequence or one result of cyanidation in this type of sample. So it can be a challenging analytical task to measure cyanide. So the methods for the determination of cyanide are defined in those methods that you saw by the relative strength of the metal complexes. So from an analytical perspective, cyanide compounds are broadly classified into three categories: total cyanide, available or weak acid dissociable cyanide, and free cyanide. And this is just a simple breakdown starting with free cyanide and some of the more simple cyanide compounds, which are readily soluble or relatively insoluble, but rather easy to determine. As you get up into the weak metal cyanide complexes and the moderately strong and strong metal cyanide complexes, then these become a bit more difficult to determine just by the fact that these do not break down very easily without taking steps to release the cyanide so that you can measure it. Again, graphically, we start with total cyanide, which includes everything in this direction. And we have available cyanide to the weak or moderately strong metal complexes of silver, cadmium, copper, mercury, nickel, zinc. And then lastly, free cyanide. So some of the interferences that were addressed early on with 1677 are the metallic sulfides, which react with cyanide with decreasing concentration, with cyanide decreasing its concentration. Dissolved metals such as iron and copper combine with cyanide to make it unable to leach gold. That's a consequence of some of the interferences that can be found in the sample. And just a short list of those would be nickel, the nitrates, nitrites, the sulfates, sulfides, cyanide, SO2. Generally, and these are typical values of what might be found in a process sample. So sulfide, when it's present in samples, can cause low or high cyanide recoveries. Low recoveries are caused by sulfide reacting with cyanide to form thiocyanate. High recoveries occur when volatilized sulfide distills over and reacts with colorimetric reagents and erroneously detected as cyanide. This is one of the primary difficulties with the other techniques that is not present with the gas diffusion and amperometric detection technique, because this step, this distillation step, is not present in our technique. So distillation of samples containing thiocyanate can result in low cyanide recoveries. thiocyanate decomposes to oxidized sulfur compounds during distillation. The oxidized sulfur compounds react with cyanide in the absorber solution and cause a negative bias. So the whole distillation step can cause any number of difficulties with the measurement of cyanide. And then lastly, samples containing the thiosulfate salts can react during acid distillation to form cyanate compounds and cause a negative bias. Again, all these result as a result of the distillation step, which is completely removed in a gas diffusion amperometric detection scheme used by the OI analytical instrumentation. And nitrate, nitrite, organic compounds can react with acid distillation to form cyanide and cause a positive bias. So again, this distillation step causes all sorts of difficulties for the determination of cyanide in these types of matrices. Other interferences, wastewater effluent samples that have chlorinated and then dechlorination using sulfur dioxide will contain sulfites. Acidification of sulfite during distillation that forms H2SO3 that decomposes to sulfur dioxide gas. This SO2 gas is absorbed in the scrubber solution along with hydrogen cyanide forming sodium sulfate. The stream of air passing through the scrubber contains sulfite, dissolved oxygen, and cyanide ion. The sulfite and oxygen will oxidize cyanide ion to form cyanate ion, resulting in negative interferences. This is particularly true in wastewater samples that have been treated. Again, the techniques that we employ eliminate these types of interferences. There. So there are a number of known interferences associated with cyanide methods that employ an acid distillation step. As US EPA has recognized solutions in their literature, Solutions to Analytical Chemistry Problems with Clean Water Act, it notes next to oil and grease, cyanide is the pollutant for which the most matrix interferences have been reported to EPA. And this is true. It's sometimes very difficult, particularly in a wastewater stream, to analyze for cyanide. So for accurate results, it's important to select an analytical technique and method that are free from these interferences. And that's one of the major advantages of the gas diffusion amperometric detection method, because it does eliminate a lot of these interferences caused by the distillation step. And again, distillation is not the only technique. There are other methods for determining cyanide. ISO 6703-1, it uses a digestion with pyridine and barbituric acid. It's applicable to water containing less than 100 milligrams per liter cyanide. Dilution is required to bring the cyanide concentration into this method. Actually, it is a titration method with photometric detection, and there are a large number of ions and compounds that interfere with this method in the titration step. Again, these are not present in our technique. 4500-CN. There are several methods within this method for determining cyanide species and concentration. Total cyanide after distillation, amenable cyanide, free cyanide, weak acid dissociable cyanide, all require different techniques within 4500-CN. These could be titrometric, colorimetric, or ion selective electrode analysis for the absorption of liquid generated from different techniques of the cyanide species. So while this method is applicable to many of the various forms of cyanide, the difficulty remains is that there are different techniques within it for each one of these. The advantage, again, of the gas diffusion technique is there's one technique that is capable of measuring all of them with, some modification to perhaps the reagents, or in the case of total cyanide, the addition of a UV digester. But that's it. The basic premise for the whole technique is the same across all of it. And then ISO 14403 is used for the determination of cyanide in groundwater, drinking water, surface water, leachates, wastewaters. Seawater can be analyzed with possible changes in sensitivity and adaptation to reagent calibration solutions. Again, some of the known interferences: aldehydes, nitrite, oxidizing agents, sulfites, surfactants, thiocyanate. So multiple interferences may require analysis of a series of laboratory fortified sample matrices to verify the suitability of the chosen treatment. I took that directly from this method. Again, as we know, it can be one of the more difficult species to analyze for, cyanide, that is. So that was a quick run through of the interferences that were associated with other methods that were available prior to the creation of method 1677. And it was those reasons that the development of the method was initiated in the first place. And from 1677 and building on that, then the method 6888, 7511, and other variants were created and adopted by regulatory agencies, because it does have the capability of eliminating many of those interferences and providing a more accurate and reliable determination of cyanide in a wide variety of sample matrices, going from process samples to environmental samples, wastewater samples, etc. So lastly, I'm going to cover briefly in the minutes that I have remaining, the FS 3700. Here's a picture of the current offering. FS, if it's for cyanide, this might change to CN 3700. It's an advanced continuous flow analyzer designed to improve laboratory productivity and wet chemistry test procedures. So here on the left, you see the auto sampler, the pump, and the chassis of the instrument. And we're going to go into the various bits and pieces that make up this instrument. So OI Analytical has been in the business of flow injection analysis, or CFA, for many, many years. And this is the latest offering, but it's building on the previous platforms, AlpChem, FirstStork, CN Solution, FS 3100, and the Flow 4. So this is just the latest in starting all the way back to the 1990s as far as our involvement in running these methods. It can run segmented flow or FIA methods. This one has a new user-friendly interface. So building on the previous versions of WinFlow, it incorporated a lot of the user requested features. It's compatible with all the current operating systems and connect via USB from any computer and actually many tablets. The various pieces of it: there is an automated injection valve installed in the analysis module chassis when required for running FIA. These would be the valves here. And each chemistry has its own cartridge, which comes pre-assembled with all the components that are necessary to run that particular chemistry, whatever that happens to be. So what it would, if the valve is necessary, say for FIA, and depending on what detector is necessary, you swap out the cartridge and then connect your pump tubes via the pump to your reagent containers. And that way you can pull them in and out to do different types of analyses. So by ordering a channel, it offers a modular, flexible hardware design for a wide variety of different types of analyses, not just cyanide. So on these, if the method requires heating or UV digestion, as we've seen for total cyanide, the UV digester is placed underneath the cartridge, underneath in the chassis underneath the cartridge. So the FlowView software provides user programmable control of both the UV lamp and the heater cartridges. Either photometric or amperometric detector modules plug into the 3700 and supports the various methods that employ these types of chemistries. And then again, and lastly, there is an expanded range photometric detector and auto-scaling software to catch some of these off-scale samples that might happen to happen. So in a single calibration curve, you can range from low ppb to high ppm concentrations. And here is just a blown up view of an entire channel. So everything you need is included here. The valve, the cartridge, the detector. They include the gas diffusion modules, heaters, UV lamps, everything that's needed to perform the analysis in this one kit. Very popular configurations for the instrument in the mining industry is OI 1677 available cyanide and 7511 total cyanide. And there is an application note available for that. So you can put both of those in the same instrument. As I've touched on earlier in previous slides, really at the heart of the cyanide determination or the cyanide analysis is the amperometric flow cell. And it is, in our opinion, the best amperometric detector on the market. It uses a silver electrode that responds selectively to cyanide, which is just at the bottom here. This is not a third-party detector. This is an OI design manufactured only by OI. It has improved cell design and upgraded electronics. So we have a reference electrode, the working electrodes, and counter electrodes at the bottom closes the loop of the detector. And as I mentioned, it's used on both the laboratory and online instruments. The only difference between the two, all the other components are the same. There is a membrane that separates, or a gasket, if you will, that separates these two halves of the amperometric cell. When we do the higher level applications for the mining industry in particular, we use a slightly narrower or thinner membrane to separate here because we don't need as much volume passing through this across the electrode. For higher or lower concentrations, like we might see on the laboratory instrument, a slightly thicker membrane to give a bit more volume in this and a bit more signal from it. So these are just some of the available cyanide. 1677 available cyanide by 6888, total cyanide by 7511. And these are some of the other ones, just a short list of some of the other ones that are available on the 3700 platform. And with each instrument, and I'll show a number of these, this is part of the abstract, we call it, from the laboratory methods. Excuse me. This gives the channel part number, the cartridge part number, the range, the rate, precision, the method detection limit for each method, a short diagram as we've seen earlier of how the instrument is plumbed, and then background on the method itself and which regulatory methods this is going to conform to. So in this case, 1677, 1677 for drinking water, 68, 88, 09 is what it conformed to. So each one would come with this description of what this particular method or this cartridge is capable of doing. Each one also comes with the calibration data and both precision and accuracy for all of the calibration standards. In this case, would be a low-level calibration method. OIA stands for OI Analytical. And lastly, other data that comes with the instrument in the method is all of the information, when this particular cartridge or this particular method was calibrated. So this gives the background information of what the method should be capable of. And this could be very important for validation purposes because there is a reference set of data that comes with each method on the 3700 that gives you the basis for what should be expected from that particular method. Again, this is another one specific for 6888 and a different range. Here we have 5 micrograms per liter to 0.5 milligrams per liter. The same information is available of what the precision MDL for this particular method should be. And this one, again, conforms to deliver directly when the ligand exchange reagents are used in 6888. The same type of information is available in terms of the calibration in this particular method. And once again, the results from the calibration curve and what you can expect. And I think I have one more. And lastly, this is ASTM 7511-12, which is the total cyanide method. We have the parameters for this particular method, how the plumbing would be arranged on the system. This is a segmented flow method. You can see by this, the air injection here and the reagents, necessary reagents for this particular one. And once again, the calibration data with the expected precision and accuracy. And here we have a list of different consumable part numbers that you might need. And lastly, as with all of our methods, all of this background information is supplied so that you do have a reference set of data to which you can refer of how this method should work in your application. In summary, I'm glad I stayed on time. The US EPA method 1677, method 6888 accurately measures available cyanide, precious metal, leaching, and detox solutions. These methods are inherently simpler in their approach than distillation methods and generally free of interferences. In some cases, there are some pre-treatment steps that we might have to take depending on, particularly with sulfide concentration. An online cyanide analyzer for measuring available cyanide in leaching and detox solutions by these methods, 1677, 68, 88, 75, 11 is available, has been available for quite some time. And the CN9310 is deployed for online measurements and process control. It can be used as a benchtop analyzer for grab samples. That's something it's capable of doing. And it has been deployed in the monitoring of surface water streams surrounding a mine for environmental protection. So it has a lot of flexibility because it has a lot of range and capability from high-level cyanide to very low levels of cyanide as well. That's why it's particularly useful for environmental type samples. So with that, I'd like to thank you for your attendance and for for having me for this webinar. I'm sure that if there are any questions, you can contact your local representative for more details, and you're always welcome to contact me directly. You have my email address down there at the bottom, and I would be happy to answer any questions or entertain any questions that you might have now.
Yeah, John, thank you very much for your presentation. There are a couple of questions related both. What are the maintenance schedule for this instrumentation, and how long lasts the gas diffusion membrane?
Well, let me see. Aside from, of course, I'll talk about the online instrumentation first. There is, of course, you have to be able to, the consumable portion of it is keeping up with to making sure that the reagents are always filled and keeping them refreshed. And the gas diffusion membrane may be dependent upon the application in some instances. Generally speaking, it has been my experience that we have not had to replace a membrane, but say twice a year. All of our instrumentation we do recommend yearly preventive maintenance activities for various things. That is highly recommended. On the process side, I think their particular attention does need to be played in terms of how we handle the sample and how we get the sample into the instrument. For the cleaner samples, this generally does not necessarily pose too much of a problem. For the slurry samples, the sample inlet system, that device does a very good job of screening out particulates. And now it was difficult to see, but in addition to the filter element around the sample probe that goes into the slurry tank, there's also an additional filter on the sample inlet device that the sample flows through. So we have dual stages of filtration to keep out particulates, because it would be particulates that we would want to keep out of the analyzer. So again, I have seen gas diffusion membranes last upwards of 6 months, even in a process application. For laboratory, I don't have, to be honest, any hard and fast, but I would think, information on that, but I would think it would, sometimes it just depends on the frequency of samples run. If it's running continuously, then I would think we'd have to see the similar performance as we do on the online instrumentation. And then other maintenance, I'm more knowledgeable on the process side because I work primarily on the process side. A lot of that maintenance generally has more to do with the sampling system than it does the analyzer itself, because we're dealing with a sample directly, say, out of a slurry pit. The membranes themselves, I mean, the filter elements around the sample probe generally must be changed probably once a month, just depending on the nature of the slurry that we're putting them into. But once a month is typical. And if you saw from the diagram, they are made to be serviced because we know that's going to have to be serviced. So you pull the probe out, you unloosen the clamp that holds it on, you pull the old sock off, rinse the probe off, put on a new one, tighten it down, drop it back in again. You can expect probably to do that once a month. And then on the instrument side, aside from keeping up with all the consumables, membranes and the gas diffusion membranes, I've seen go upwards of 6 months.
Thank you, John. Thank you for the answer. There's another question regarding FS3700. If it is possible to develop applications, we don't have a channel or cartridge available.
What was the question again? Let me make sure I understood that one.
Sorry, the question is, what if there is not a cartridge developed for some application? Can it be done a new application cartridge?
Oh, interesting question. Yes.
Let me answer.
Yeah, I think we could.
Yeah, we used to have a what we call it, the research cartridge.
Yes.
A combination of all type of components that would allow you, the customer to just kind of develop a method. I'm not sure if we had one ready for the FS3700, but I'm sure we could supply one. Let me check on that.
Yeah, I'm glad you did in there, G, because I remember hearing about that particular cartridge.
Okay, thank you. And one question by me. You mentioned and you show, John, a correlation between the lab equipment and the process equipment.
Mm-hmm.
What is the advantage of have the same results in both systems?
Okay. It has been my experience that in not only mining applications, but really in any application, in many instances, the laboratory has the final say in as far as reportable numbers are concerned, and that by I mean reportable to some type of regulatory agency, as far as what the concentration of a sample might be. I mean, this holds true not just for cyanide. I've seen the same thing for total organic carbon. I've seen the same thing for volatile organic carbon in other species, in other measurements where any parameter is regulated by some type of agency. In this country, it would be EPA, or in the various states, it could be state EPAs. It could be state and local guidelines. What is generally reported is the laboratory result. And that, again, that holds true also, I believe, for cyanide. As an example, in the United States, we have deployed a CN9310 as an online measurement tool in a completely different application. It was a metal plating application where cyanide is used in the metal plating process. But these particular plants have both online instrumentation and laboratory instrumentation. So what happens is if the online instrument begins to detect a trend in the increase of cyanide that is going through their wastewater treatment process before it's being discharged into the community, then that alerts someone at the plant to take samples and then once again measure them in the laboratory for final verification or absolute verification, because ultimately that's what's going to happen downstream of a plant is someone somewhere is going to draw an environmental sample and test that on a laboratory piece of equipment, not an online instrument. And that becomes the result, if you will, that's going to be used to provide, the information as far as, if we're talking about some type of, discharge permit violation. So having both in the same place, particularly if both are using the exact same technique, it tends to remove some of the differences that might occur because you're using different techniques. Of course, if both techniques are calibrated and are running properly, yeah, ideally we should get the same answer. But sometimes there can be differences, and having both in the same place eliminates a lot of that variability and eliminates a lot of the possible differences you might see in each one. Not to mention, as far as our equipment goes, some of the parts are interchangeable. The reagents are the same. The amperometric flow cell with a slight modification depending on the range is the same. The gas diffusion membrane is the same. So it shares a lot of commonality between the two in the event that, say, a lab and operations in a plant are sharing resources as far as instrumentation goes. So there are a lot of upside advantages of having both in the same place.
Okay, thank you very much. I don't see any more questions. Thank you very much for your presentation. Thank you everybody for coming for this webinar. Gracias a todos, muchas gracias. Gracias a John, a Giovanna de OI que nos han apoyado con este seminario. Les recuerdo que el seminario queda grabado en nuestra página de YouTube, por si alguien quiere volver a verlo y repasar pues toda la información que nos han compartido. Muchas gracias por su participación y les informaremos para más seminarios. Gracias a todos. Thank you everybody. Have a good day.
Thank you.
Thank you.
Thank you. Bye-bye.
Bye-bye.
Recording